Hi, it's Ben Holcomb here, Associate Professor in Mechanical Engineering. I'm back down here in the Vibration Lab, our experimental research facility at Botany UTS Tech Lab. And this is the third in a series of videos about how to use the automatic modal impact hammer. And as you can see, this setup here includes the Polytec PSV scanning laser vibrometer. If my cameraman friend just comes down here, we can see the automatic impact hammer. And those of you that have seen the second video will remember where we left off. I'd set it up on the bench top. I'd shown the use of the interface to control the impact hammer. I talked about the way that we can adjust the parameters such as the velocity of the excitation, the stop angle, and the time interval to allow us to get clean impacts on our target structure. If we have a look at the sample that we're interested in today, it's a relatively simple plexiglass plate with 3x5 grid of discretized points, and as you can see, the automatic hammer is tapping the underside of the plate, and we've currently got 1 second separation between the impacts. We can change the separation between the impacts in the interface to allow us to collect good measurement data such that we can effectively replace a manual impact hammer with the automatic hammer. If we come back to the software side here, I'll have a look at the PSV software in here, and I can just stop this one or restart it, and when I restart it here, we'll see these are my impacts here. It's a relatively low level force impact, but if I zoom in, we can see the impulsive excitation. Relatively coarse temporal resolution at this moment. I've only got an acquisition bandwidth up to approximately 1 kilohertz. And here's the response being measured by the laser Doppler vibrometer on one of the measurement points. And you can see the contribution of a series of different resonant frequencies at the various different resonances. If I go back to the SAM interface, then I'll probably just reduce the time between impacts from 1 second to 2 seconds. That slows down the repetition rate. And to get a bit of a better look at the impulse in particular, I'm going to change the bandwidth in the acquisition software to 10 kilohertz. And as a result of that, then now I have very short sample time, so I'll change also my spectral lines to not 100,000, but 12,800. That's a 1.28 second time block. So my 2 second repetition is at least, it has to be greater than this value, otherwise I'm doing multiple impacts within one block of time data. So as you can see now, my duration of the impulse of the measurement is 1.28 seconds, and here's my impulse here. And if I zoom in again, we've got a little bit more temporal resolution. We can still see the sample frequency here. So let's increase that bandwidth again to, I'm very fortunate to have up to 100 kilohertz sample frequency, but we'll go for 50 kilohertz and 50,000 lines. So again, around about a second. Zoom in, and now we should see a very nice fine temporal resolution here on this. And indeed, you can see if I also auto scale, got quite a very nice looking impulsive shape, no ringing afterwards. Of course, this is an impact hammer, so there is some measurement coming from the force transducer even after the hammer tip has come away from the structure. So some of this signal is not actually what's going into the structure. There are some advanced settings to be able to take care of that. And there's my response measurement up here. The other thing that we should have a look at then is the FFT, of course. So we're looking for, when we do modal impact measurements, a very nice looking wide frequency range of excitation. This is the sort of characteristic downturn, although I'm looking now in magnitude. So if I look at magnitude in dB and auto scale, then we can see the sort of typical characteristic we have from a modal impact hammer, where we have this first like hump, and then a bit of a dead area here and another hump, and so on and so forth. So for a perfect impulse, we'd see a flat line. For something that's perfect, so it's got some width, we see this characteristic shape, this sort of lump shape hills. And this is the useful bandwidth in here. So approximately 1 decade down from the maximum here is our sort of useful available bandwidth. So we've got quite a large scale on here, but if we sort of were to measure up to around about 7.5, 8 kilohertz, this would be a pretty good useful range. The duration of the impulse is controlled, is a function of the stiffness of the tip, the combination of the tip stiffness and the sample stiffness, the local stiffness, and as it currently is set up with a steel tip and an acrylic plate, the duration of the impulse is, on the order of about well, this is 50 milliseconds and 60, so around about a millisecond. If we were to replace the tip with a rubber tip, a softer tip, then we would increase the duration of the impulse and we would reduce the frequency range over which the sample was excited. So this lump here would move to the left. If we made the tip and sample stiffness higher, then we would widen the frequency range of excitation. Let's have a look now if I reset the A to D parameters back to around about a couple of kilohertz and adjust the spectral lines accordingly. So back to 1.6 seconds of excitation, 3,200 lines. What we really are interested in is to get good FRFs. So up here I've got an FRF, I'm showing vibration and reference. This is the response measurement divided by the impulse excitation, the force transducer measurement, and very nice coherence function here as well. We're looking for coherence to be 1 across the entire across the entire frequency range. So there are a couple of resonant frequencies which we can see within this spectrum here. Actually, this sample has a couple of close modes, very close together, so there's sort of a couple of peaks in there which we can maybe just about pick out. They're basically contributing to the same peak in the spectrum here, another couple of resonances up here, and wherever we have resonant frequencies, we want to ensure that we have good coherence function. And coherence comes about as a result of having a well-defined excitation peak within a sensible frequency range, good signal to noise ratio on both the excitation and the response, and that's how we get good coherence. That's how we can go on to get good measurements with our automatic impact hammer. And that's it for this video. Thanks a lot.